Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it. This is Chapter 7, Section 1. And Chapter 7 in general is Applications of Integration. And 7.1 specifically is area of a region between two curves. All right, so here we go. So let's say that I have two functions, right? I have this function here, and I've got this other function over here, something like this, right? And what I want to do here is I want to find the area in between these two curves, in between A and B. All right, so I want to find out that area that I'm shading in green. Well, it turns out that what we can do here is that, well, let's do the following. And what we can do here is we can start with the bigger area. And so here we go. We're going to start with the bigger area. Oh, that's not what I meant to do. Here we go. And then subtract the smaller area. So in here, what we can say is we can get rid of all this top stuff. And we're going to subtract this region down here, right? So that's the main idea there. That to figure out this area over here, what we're going to do is take the bigger area under the bigger curve and subtract the area under the smaller curve. All right. So let's formally define that area. If f and g are continuous on the interval from a to b, and g of x is less than or equal to f of x for all x in that interval from a to b, then the area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b is the following. So, well, before I tell you what it is, let's build it, right? So let's look at what it would be. So what we're going to do here is we're going to look at this and say, well, let's figure out what if we have just one rectangle here, right? And in here, that yellow curve represents f, and the blue curve represents g. So in here, I'm taking just one rectangle, right, to represent stuff here. In this representative rectangle, again, on top, we have f of x, and on bottom in blue, we've got g of x. But in here, in this representative rectangle, what is the height of it? Right? Well, the height of it would be, well, at this point, whatever this point is, right, it would be the value of the top function minus the value of the bottom function. So in here, we could say the height would be equal to f of x minus g of x at that specific point. I'm going to call, if I call this x sub I, these become sub i's. All right. And, well, what is the width? The width here would be delta x. So overall, if I want to have infinitely many of these rectangles in here, right? Because if you recall, that's how we add up the area there. But we're going to say the area is going to be the limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I minus g of x sub I delta x. But we know that in here, that becomes just simply the integral from a to b of f of x minus g of x dx instead of delta x now. All right. So that's the visual there. Now, I don't want you to think of this as f minus g because it very much depends on what the value of what functions they are. But I want you to think of it this way. So I want you to think of it as the integral from a to b of the top function minus the bottom function. All right. So that's how I want you to think about this integral, the top function minus the bottom function. So let's do some examples here. All right. So here we go. Example A. So we're gonna say find the area of the region bounded by, we're gonna say y equals 3x squared plus 7, y equals negative 2x, from x equals 1 to x equals 3. All right. Now in here, I'm going to start without the visual, all right, because I want you to see what we would do when we don't know what this graph looks like, all right. The visuals are great, but what if you didn't have a visual? Well, let's see. In here, we're saying that we're working between 1 and 3. So we're working between 1 and 3. So what we want to do is we want to plug in any value in there into both of these functions to figure out which function's on top. So I'm going to call this y sub 1 and y sub 2. So in y sub 1, if I evaluate it at x equals 2, what do we get? Well, we end up with 3 times 2 squared plus 7. 2 squared is 4 times 3 is 12 plus 7 is 19. If I evaluate y sub 2 at x equals 2, well, I end up with negative 2 times 2, which is negative 4. So in here, these two essentially tell us that y sub 1 is bigger than y sub 2. So y sub 1 would be our top function. All right, so y sub 1 is top and y sub 2 is bottom. So now we're going to say, well, our area now is the integral from 1 to 3, right? Because that's the interval that we were working with, of the top function, which was 3x squared plus 7, minus the bottom function, which was negative 2x, and all of this dx. All right, so let's simplify that a little bit, just so that we have a simple integral, and I end up with 3x squared plus 2x plus 7 dx, right? And if we integrate this, well, what do we get? We say the integral of 3x squared is x cubed, plus the integral of 2x is x squared, and the integral of 7 is 7x. And this gets evaluated from 1 to 3, right? So what do I get now? Well, I get, plug in 3, so 3 cubed plus 3 squared plus 7 times 3 minus, plug in 1, 1 cubed plus 1 squared plus 7 times 1, right? And then what does that give us? Well, 3 cubed, excuse me, is 27 plus 3 squared, that's 9. 7 times 3, 21, minus 1 plus 1 plus 7. And what do we get now? Well, 27, well, 9 plus 21, that's 30. 30 plus 27 is 57. 57 minus 9 gives us 48. All right, so the area there is 4 units squared. All right, 48 units squared, excuse me. Now I can give you the visual. Now that we already have an answer, let me give you the visual. So this is the visual. And again, notice how we did that problem without at all looking at what the visual was. And essentially it looks something like this. Negative 2x looks like this. Alright, so that's y equals negative 2x. And then the other one, 3x squared plus 7. That looks something like this. Alright, where this is a parabola. And what we found is that the area between here, starting at 1, going all the way up to 3, this area is an area of 48 units squared. And maybe I'll write that as 48. Actually write the word units. Right? And by units we mean, well, what if we were working with feet, it would be square feet. If we were working with meters, it would be square meters, so on and so forth. All right, next one. B. Let's say that I had y equals, or y sub 1 equals x cubed over 3 minus x, and y sub 2 being just x over 3. All right, and we're going to do this from 2 to 4. So again, to figure out which is the top one and which is the bottom one, what we want to do is plug in the value in between these two. All right, so let's say that I plug in 3. So I'm going to evaluate y sub 1 at x equals 3, and I end up with 3 cubed over 3 minus 3. So that's 3 cubed 27 over 3 is 9 minus 3 is 6. If I evaluate y sub 2 at x equals 3, I end up with 3 over 3, which gives me just 1. So again, y sub 1 is bigger in this case. So what we do now is our area is the integral from 2 to 4 of the top function, x cubed over 3 minus x, minus the bottom function, which was x over 3. And all of this dx. And what does that give us? Well, this negative x and negative x over 3, they can be combined. So we end up with the integral from 2 to 4 of x cubed over 3 minus 4/3 x dx. And if I integrate here, I end up with x to the 4th over 12 minus 4 over 6 x squared. This 4 over 6 reduces to saying 2/3, right? Evaluated from 2 to 4. Plug in the top, so I have 4 to the 4th over 12 minus 2/3 times 4 squared, and then minus, plug in the bottom, 2 to the 4th over 12 minus 2/3 times 2 squared. And, well, what does that give us? Well, 4 to the 4th. 4 to the 4th, that's 4 times 4, which is 64. And then, 4 times 4, which is 16. Then times 4, which is 64. And then times 4 again, which is 256. So we get 256 over 12 minus 4 squared, 16 times 2 is 32. So we have minus 32/3 minus 2 to the 4th, that's 16. 2 squared times 2, well, that's 2 to the 3rd. So I end up with 8/3. Combining like terms here. So let's say I've got 256/12 minus 16/12. That's 240/12 minus negative 32/12 minus a negative 8/12. Well, I said that wrong. Negative 32/3 minus a negative 8/3. Minus negative is plus, so negative 32 plus 8 is negative 24. So we get negative 4/12. Negative 24/3. And from here, 240 divided by 12. Well, 12 goes into 24 2 times. So 12 goes to 240 20 times. 3 goes into 24 8 times. giving me an answer of 12. And again, units squared. And I'll quickly do a visual here, right? This is essentially what we've got, at least in this region. It's something like this and like that. All right, and what we found here was from 2 to 4. Oh, I should zoom this out a little differently. That's, I guess we can do this way. That's fine. Here's 2, here's 4. All right, and what we found was this region. Not drawn to scale, of course. All right. All right. So in both of these examples, I told you where the x values were, right? I told you from 2 to 4. And similarly over here, I said from 1 to 3. But let's see what happens when I don't give you any bounds. What do we do there? So next one, example C. And this is going to be y sub 1 is equal to 2x plus 5. And y sub 2 equals to x squared plus 2x plus 1. So yes, notice again that in here I did not give you any bounds, right? I didn't say from what x value to what other x value. Well, in here we're just implying that our area is going to be just between these two functions. So what we need to do here is figure out where they intersect. And how do we do that? We set them equal to each other. So let's say I've got x squared plus 2x plus 1, set it equal to 2x plus 5. Move everything to the same side. X squared minus 4 is equal to 0. Right, subtracted 2x, subtracted 5. And factor, so x plus 2 times x minus 2 equals 0. So that x equals negative 2 or x equals 2. All right, so that gives us where they intersect at those x values, at negative 2 and at positive 2. Now to figure out which one's bigger within that region, well, we just need to plug in one of the values in between there. So let's say y sub 1, let's evaluate it at x equals 0. So when I do that, well, I end up with 5. And y sub 2, when I evaluate at x equals 0, well, when I do that, I end up with 1. So in here, y sub 1 is our top function, and y sub 2 is our bottom function. All right, so now, what do we get? Our area is going to be the integral from negative 2 to 2 of the top function, which we said was y sub 1, so 2x plus 5, minus the bottom function, y sub 2, which we said was x squared plus 2x plus 1 dx. And what does that give us? Well, let's simplify this a little bit. So we end up with the integral from negative 2 to 2 of, combining like terms here, I end up with negative x squared plus 4, right? This 2x minus 2x goes away. 5 minus 1 is positive 4, and negative x squared is right there. And when we integrate this, well, what do we get? We end up with negative x cubed over 3 plus 4x, evaluated from negative 2 to 2. And when we plug in these values, we'll plug in the top first. So I end up with a negative of 2 cubed over 3 plus 4 times 2 minus the negative of negative 2 cubed over 3 plus 4 times negative 2, which now gives me, well, 2 cubed is 8, so I have negative 8 over 3 plus 4 times 2 is 8 minus negative 2 cubed is negative 8 with a negative in the front, becomes positive 8, so I have 8 thirds, and then 4 times negative 2 is negative 8. Negative 8 thirds minus 8 thirds, that gives me negative 16 thirds. 8 minus negative 8, that's 8 plus 8, which is 16. So, and what we need to do now is come up with a common denominator, which is 3. This 16 becomes a 48 because 16 times 3 is 48, and then negative 16 plus 48 is 32. So we end up with 32 thirds units squared, right? All right, so let's do one more that's similar to this, and then we'll kick it up a notch. So let's say that I have so D, example D. All right, so we have y equals x minus 1 cubed. That's y sub 1 equals that, and y sub 2 is equal to just x minus 1. All right, and what we want to do here is we want to see we want to find the area between those two curves, right? And to do that, well, we got to figure out where they intersect. So let's see. Set them equal to each other first. So I have x minus 1 cubed is equal to x minus 1. Move this to the other side. X minus 1 cubed minus x minus 1 equals 0. I see they both have an x minus 1. Factor that out. X minus 1 times x minus 1 squared minus 1 equals 0. Expand this. X minus 1 times, well, if I expand that, what do I get? I get x squared minus 2x plus 1, and then we have this minus 1. Combine like terms here, right? If I combine like terms here, what would I end up with? So I have x minus 1 times x squared minus 2x. And then plus 1 minus 1 goes away. So fully factoring this, I end up with that, right? So, oh wait, look at that. I made a mistake. That 2 should be, that 1 right here should be a 2. All right, so now, so what does this tell us? That gives us now the values of x equals 1, x equals 0, and x equals 2. So we've got 3 places where this function intersects, where these two functions intersect. All right, so what are we going to do now? Well, that means we need to split up our interval between 0, 1, and 2, and then see which functions on top and which ones on bottom at each piece. So for example, let's say that we have in here at 1/2. We're going to see what happens there, right? So 1/2 minus 1, that's negative 1/2. So let's see. So at x equals 1/2, we had that y sub 2 was negative 1/2, right? Because it's 1/2 minus 1. Y sub 1, however, is going to be negative 1/2 cubed, which is negative 1/8. So in this region, well, what's bigger, negative 1/2 or negative 1/8? Well, negative 1/8 is bigger. So y sub 1 is bigger than y sub 2. Now let's see what happens in the next region. So for example, let's plug in 3/2. Well, let's see. Y sub 2. Y sub 2, I'm starting with that one because it was just x minus 1. So 3/2 minus 1 is 1/2. Y sub 1 was that but cubed. So 1/2 cubed, which is 1/8. In here, which one was bigger? Y sub 2. So y sub 2 is the bigger one, so it's the top one. And y sub 1 is the bottom one there. So now, our area is going to be the sum of the area between the curves from each interval. Right, so I'm going to have the interval, this is going to be the integral from 0 to 1 of y sub 1, the top function, minus y sub 2 dx, and then that plus the integral from 1 to 2 of y sub 2 minus y sub 1 dx, right? The top function minus the bottom function. And just as a reminder, y sub 1 was x minus 1 cubed, and y sub 2 was just x minus 1. So what I get here is the integral from 0 to 1 of x minus 1 cubed minus x minus 1 dx plus the integral from 1 to 2 of y sub 2, which was x minus 1 minus x minus 1 cubed dx. All right. Now, in here, I don't want to expand all this stuff out, so I'm going to do a simple substitution. I'm going to say let u be equal to x minus 1. Then du would be just dx. When x equals 0, u equals negative 1. When x equals 1, u equals negative 2. And when x equals 2, u equals 1. Right? So what does that do for us now? This integral now becomes the integral from originally 0 to 1, now negative 1 to negative 2. Oh, sorry, that's messed up. That should be a 0. Negative 1 minus 1 is 0. Look at that. That should be a 0. There we go. So from negative 1 to 0 of u cubed minus u du plus the integral from originally 1 to 2, so now it's a 0 to 1, of u minus u cubed du. And well, what does that give us? That's going to give us u to the 4th. Well, let's do it on the next line. U to the 4th over 4 minus u squared over 2, evaluate from negative 1 to 0, plus u squared over 2 minus u to the 4th over 4, evaluated from 0 to 1. And well, what does that give us? Well, plug in 0, I end up with 0 minus 0 minus plug in negative 1. Well, negative 1 to the 4th, that's 1, so I got 1/4 minus 1/2, right? Negative 1 squared is just positive 1. So that's the second one there. Plus plug in 1 into here. I end up with 1/2 minus 1/4 minus plug in 0. 0 minus 0. Okay, so let's see what we get. 1/4 minus, alright, so we have 0 minus 0 goes away. This negative of 1/4 minus 1/2, that's negative 1/4. Right? 1/4 minus 1/2. 1/2 is 2/4. So 1/4 minus 2/4 is negative 1/4. Plus 1/2 minus 1/4, that's going to be 1/4. The zeros go away. Negative 1/4 plus 1/4. So this is positive 1/4 plus 1/4 is 1/2. So our answer there is just 1/2. All right. Now, in all these examples, we were doing everything originally in terms of x, right? And the reason for that is because we had functions of x, right? I have y as a function of x in both of these, in every single one of these. Every single one of these were y as a function of x. But we don't necessarily need to do functions of x. We can do functions of y. And what I mean by that is it's not just a simple change in variable. What I'm talking about is horizontal representative rectangles. All right, so let's do an example. I don't know why I said G. I think I meant E. There we go. So find the area bounded by x equals 3 minus y squared and x equals y plus 1. All right. So in here, well, we're gonna start this the same way, and by that I mean I'll give you Well, let's start with the visual, but we are going to start this the same way. But this time I'll give you the visual first, just so you can get an idea of what's going on here, right? So I've got 3 minus y squared. 3 minus y squared looks like this, right? It is a sideways facing parabola, all right? And maybe I should have done that in yellow. That's okay. The next one, y plus 1. X equals y plus 1. That looks like this. It is this line. This is x equals y plus 1, and this is x is equal to 3 minus y squared. All right. Now, in here, we still want to do the top function minus the bottom function. But now, because we've got functions of y, we can imagine having this guy here. All right. And in here, to him, which is the top function? Well, that would be the top function. And this would be the bottom function. Right? So that's what we want to think about it. All right. Now, that was doing this graphically, but let's figure things out without the graph. We already have an idea of which is supposed to be the bigger function and the smaller function, right? But we still need to figure out what this value is and also what this value is, because we got to figure out where we're working. All right. Now, to be a little bit more exact here, if you really want to think about the representative rectangle, well, let's do this. So here's my representative rectangle. The width here is going to be delta y now, but the height in this case is going to be, well, this function. So I'm going to call them x sub 1 and x sub 2. So it's going to be x sub 1 minus x sub 2, right? Those two different functions there. So you could think of these as, well, if I call this f of y and this g of y, you could think of this as f of y minus g of y, all right? And at that point, we would say, well, the area is going to be the integral. Actually, well, before that, we still got to figure out where they intersect. So let's set them equal to each other. 3 minus y squared is equal to y plus 1. I'm going to move everything to the right. So 0 is equal to, well, this y squared over. So y squared plus y. 1 minus 3 is negative 2. Factoring this, I end up with y plus 2 times y minus 1, giving me the values of y equals 1 and y equals negative 2. So here this is negative 2 and this is 1. So now we can do our integral. Then the area is going to be the integral from negative 2 to 1 of the top function minus the bottom function. Oh, let's test that out before we actually do this integral. So by that I mean, in here we already know the visual, right? But what if we didn't have the visual? How would we know? Well, let's test out. So between 1 and negative 2, something that we can test out is the value of 0. So what happens when y equals 0? Well, x sub 1, this first one, I end up with 3. X sub 2, the second one, I end up with 1. So this is the top function and this is the bottom function, which made sense already, right? Because we had that from the graph. But now we know algebraically how to figure it out. Now we can do the integral. So we're going to say the integral, the area is the integral from negative 2 to 1 of the top function, which we said was x sub 1, which is 3 minus y squared, minus the bottom function, which we said was x sub 2, which is just y plus 1. Right, and dy, because our bounds are in terms of y, right, from up here. All right, so let's go ahead and integrate this. So actually, let's reduce first. Let's combine like terms. So I've got the integral from negative 2 to 1 of 3 minus 1 is 2. So I'm going to write it as 2 minus y squared dy. Integrating these, well, what do I get? The integral of 2 is 2y minus y squared over 2 minus y cubed over 3, evaluated from negative 2 to 1. Plug in the top. 2 times 1 minus 1 squared over 2 minus 1 cubed over 3 minus, plug in the bottom, 2 times negative 2 minus negative 2 squared over 2 minus negative 2 cubed over 3. That's a 3. All right. Now, let's simplify this a little bit. So we have, in the first thing here, I have 2 minus 1/2 minus 1/3. Cool. In the next part, 2 times negative 2 is negative 4. Negative 2 squared is 4, so minus 4/2. Negative 2 cubed is negative 8, so I have plus 8/3. Let's see, combining like terms. 2 minus negative 4, 6. Negative 1 minus negative 4/2. So negative 1/2 minus negative 4/2 is a positive 3/2. Negative 1/3 minus 8/3 is negative 9/3. Negative 9/3 is 3. So 6 minus 3 is 3. So 3 plus 3/2. Common denominator of 2. This becomes 6 plus 3, which is 9/2. All right. So that entire region there, perhaps I'll outline it in yellow here. This entire region has that area that we just found. All right. Cool. Next one. So that was E, right? E, maybe? E, yeah. F. So let's say that we have the function is g of y is equal to y times 2 minus y, and the function f of y is equal to negative y, right? And again, here we're doing the same exact thing as before. All we're doing here is just a different variable. All right, it's still going to be the same exact idea of the bigger function minus the smaller function. So let's go ahead and see what we get here. So I start first by setting these two equal to each other. So y times 2 minus y is equal to negative y. Put everything on the same side. I'm also going to expand. So y times 2 is 2y minus y squared, and then plus y equals 0. Combine like terms. 3y minus y squared equals 0. Factor y times 3 minus y squared, not y squared, times y equals 0. So either y equals 0 or y equals 3. All right. So that gives us the region that we're working in. So now let's see what's something in there that we can use to figure out which is the bigger function. Well, let's figure out what happens when y is 1. So what we can do here is, well, our function g, so g of 1 would be 1 times 2 minus 1, which is 1. Our function f of 1 would be negative of 1, which is negative 1. So in here, our g function is our top function, and the f function is the bottom function. So what we can do now is we can do the integral for the area is the integral from 0 to 3 of the top function, which was g, and that was y times 2 minus y, minus the bottom function, which was f, which was negative y, and not dx, dy. Expanding this a little bit and simplifying, well, I'm subtracting that's negative y, which is that's essentially what I did over here. So I know that I'm going to get 3y minus y squared dy, giving me, well, the integral of that would be 3/2 y squared minus y cubed over 3, evaluated from 0 to 3. Plug in the top. So I have 3/2 times 3 squared minus 3 cubed over 3. minus 0 minus 0, right? Plugging in that 0 into the y's does nothing. So at this point we say, well, what do we get here? 3 squared, that's 9 times 3 is 27. So 27 halves minus 3 cubed is 27. 27 over 3 is 9. Common denominator is going to be 2. Leaving this to 27 and changing that to an 18. Giving me an answer of 9 halves. All right. That's coincidence that that's the same answer as the last problem, 9 halves. Cool. Didn't even realize that. All right. So we got an area of 9 halves, but now let's look at the visual for this one. Notice again we started without a visual. All right. So let's see what the visual is here. So it looks something like this. All right. Oh, that was awful. Let's try it again. Yeah, that's better. Yeah, that was not great. Where this value up here, it's at 3. And oh, look at that. I did my sideways parabola all wrong there. So it should look like this. Something like that. All right. All right. So what we found there was what I'm gonna this region right here. We found that area. All right. Units squared because it's an area. All right. So I mean, these last couple examples were just to show that we can actually do things in terms of horizontal rectangles, right? Functions of y, not just functions of x. So the same exact idea. That is the end of 7.1, but I will be making, but there will be also another video where I do advanced examples of area, all right, which I highly recommend that you do watch. So that was the end of 7.1. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.